Dear students, another famous discrete random variable and distribution which is extensively applied is the Poisson distribution introduced by Simon D. Poisson. It is often used to model frequency with which an event occurs during a particular period of time. As examples, number of patients who arrive at an emergency room between 6 a.m. and 7 a.m. Number of telephone calls received per day at a switchboard. Number of misprints in a book. Number of earthquakes occurring during a period of 1 year. Examples of Poisson distribution. That is, examples where you can use Poisson distribution to model the frequency, the probability with which such events occur. Now, consider the example, the pin-making example of lathe. That is, the lathe which produces pins. Actually, Poisson distribution is used to describe rare events. Rare events. Events which happen rarely, like number of patents received by a company during a given time, number of papers published by a professor during a period of 1 year, etc., etc. To consider this using a simple example, consider the lathe producing pins. On rare occasions, the lathe will produce the gem of a pin, a high quality pin. The gem of a pin which is so perfect that it can be used for very special purpose. And to make the case specific, suppose that the lathe produces 20,000 pins and has only 1 by 20,000 probability to produce the gem of a pin. The probability of producing such a high quality pin is very low. And suppose that you are interested in the number of perfect pins produced. And if you try to calculate the number of perfect pins produced using binomial distribution with n equal to 20,000. 20,000, P is equal to 1 by 20,000. Only one good pin out of 20,000. And probability is only 1 by 20,000. Calculation will be very difficult because n is very large, p is very small. Also, binomial formula calls for n factorial because NCX calls for the use of n factorial. It is equal to n factorial by x factorial into n minus x factorial. So you cannot calculate n factorial. This will be a very huge number. Also, you cannot calculate p raised to n minus x because n is so large. Calculation is not possible. So you cannot calculate the binomial formula because n is too large, p is too small. However, we can calculate expected number of perfect pins produced as n into p is equal to expected number n into p is equal to 20,000 into 1 by 10,000 is equal to 2, which is neither too large nor too small. So binomial probabilities cannot be calculated because n is too large, p is too small. But we can calculate expected number of perfect pins. Now it turns out that as long as expected value np, mu is equal to np, n into p, mu, expected value of say x mu is equal to np. So as long as expected value mu is equal to np is neither too large nor too small, say lie between 0.01 and 50, lie between 0.01 and 50, the binomial formula for probability that x is equal to x can be approximated by an equation probability that x is equal to e raised to minus mu raised to x by x factorial, where x is equal to 0, 1, 2, etc. And e is equal to 2.71828. And this formula is known as the Poisson formula, and the distribution is Poisson distribution. This is the Poisson formula, and the distribution is known as the Poisson distribution. And in general, if we count the number of times a rare event occurs during a fixed interval, then the number follow Poisson distribution. So Poisson distribution is used to model rare events, and the mean is equal to mu is equal to np, and we denote it as x Poisson with the mu. X is distributed as Poisson with the mu. Now consider the variance. For binomial distribution, it is n into p into 1 minus p. As p is very small, as p into 1 minus p, as p is very small, 1 minus p is close to 0, so that variance is close to 0 means variance is n into p is again equal to mu. So we write x is distributed as Poisson with the mean equal to mu, variance also equal to mu. So Poisson distribution has only one parameter, that is mu, and it and not n and p. np mean mu, variance also same. So this is the distribution which is used to model rare events. As an example to how this is actually applied, suppose that mu is equal to mean, then probability that x is equal to 3 is e raised to minus 2 raised to 3 divided by 3 factorial is equal to 0.1804. Expected value of x is equal to mu is equal to 2. Variance is also equal to 2. This is how we calculate the probability that x is equal to 3 or x is equal to any number. Anyway, we use this distribution to model events which rarely occur. So remember these three distributions: Bernoulli random variable, binomial random variable, Poisson random variable, and the corresponding distributions.